Okay, let's do some examples of limits. And we're still really just trying to get some intuition for what limits are and what they're saying. So some of these methods are going to get faster and more advanced as we go. And some of these methods can be done very quickly by a calculator. But for now, let's just focus on doing a couple of them by hand. So we have this limit as x goes to 3 of 2x. And what I'm going to do here is play the game we played before, where I've got x and I've got f of x, and I'm going to go ahead and just, make this a little cleaner. I'm going to go ahead and just walk these x values closer and closer to 3. And so I might say start with 2, and then I might go with, say, 2.5, and I might go with 2.9, and we're going to be a little lazy here. You should probably go a little bit further. And we'll also walk them the other way and say, let's start with 4, and we'll go to 3.5, and we'll go to 3.1. And there's no limit of how close you can go, which is both good and bad. So if I was going to take this x value of 2 and plug it into this function 2x, I would get a 4. And I take an x value of 2.5 and I plug it into 2x and I get a 5. I plug in 2.9 and I get a 5.8. Okay, maybe you're seeing where this is going. If you're unsure, we could even go further. I could go 2.99, and if I plug that into 2x, I'm just doubling it. So I would get 5.98. And I can walk it the other way from the right and say, okay, if I come from a bigger number and make it smaller, well, at 4 I get 8, and at 3.5 I get 7, and at 3.1 I get 6.2, and if I didn't quite see the pattern yet, I didn't see where it's converging to, I could even go 3.01, and this would give me 6.02. And I hope if you look at these and you say, okay, as I come from the right, this is what's happening. As I come from the left, this is what's happening. As I come from the right, this is what's happening. And I sort of look and I say, all right, what are these converging to? I hope you see, and if you don't see it, then keep going, that this should equal 6. Okay, so this is meant to give you an intuition for what a limit is doing. It's looking kind of closer and closer and closer in your x values and saying what is happening to the y values. And if I wanted it to be more and more precise, I could just go further and further and further until I saw that my decimal places were sort of stabilizing, or I could average these two. And there's lots of tricks for using tables like this to get limits, for numerical approximations of them. But you might also see that there's a bit of a problem. It's hard to know when to stop. It takes a bit of time. It's a little bit confusing as to, like, well, should I take this number or that number, or what if maybe these numbers are going to start spiking in the middle and doing weird things if I get a little closer. So we are going to just start with these tables for the intuition. There's lots of good resources as to how to get a calculator to do this for you even, and you should feel free. Please do. And then we'll quickly go into other things like doing this algebraically. Let's go ahead and graph this though. So 2x, if I was going to graph 2x, then it should have a slope of 2 and a y-intercept of 0. Right? Y equals mx plus b. That plus b is plus 0. A slope of 2 means I'm going to go over 1 and up 2. Oh, and that is really all I need to draw a quick graph here of this thing. Keeping this as a scale of 1. Whoop. Something like that. Pretty close to that. If I were to look at what happens to this thing at 3, well, it looks like 3, 1, 2, 3 is right about here on this line. The line's nice and continuous. It's not doing anything weird. I could even, if I want to draw this line a little further, right, it kind of keeps going. Okay. So right there at 3, that y value is 1, 2, 3. Sorry, that was at 2. Oh, how embarrassing. Let's fix this up here. All the way up. Okay, so now at 3, 1, 2, 3, there we go. If I drew this line right, it would be right at 1, 2, 3, 4, 5, 6. Right there at 6 if I drew that right. And that's what should happen with this line, right? Over 1, up 2, over 1, up 2, over 1, up 2. I should be right at 6. Okay. So because there's no holes or breaks or jumps, we're just going to take the value of the function at 3, which is 6. And again, this will be called continuous in a little bit. Now, let's go back to something that we've already done. We've actually already done the table for this x squared minus 1 over x minus 1. We could do it again if we wanted to. I'm going to go a little bit quicker here. We could say this is x and this is f, and we could go ahead and say, oh yeah, on the left I might put in a 0 and a 0.5 and a 0.9 and so forth and so on. And then on the right, I could walk it in from the right, and I could say, all right, how about maybe a 2, and how about maybe a 1.5, and how about maybe a 1.1. And I could go ahead and fill in these tables and say, oh yeah, this is a 1. Oh yeah, this is a 3. And I could go the whole way. And again, like we did last time, we would see that this whole thing converges to a nice 2. Okay. Again, we could also graph it if we really wanted to. And if we were to graph this thing, as was pointed out at the beginning, we would get a nice line, except that that line, I gotta do it with a pencil, that line is gonna have a hole right at 1 because it's not defined at 1. Okay, so we could see that what a limit is doing is just filling in a hole. Or the third way that we're gonna be talking about as well is the algebraic way, which we saw before, which is just factoring this thing. So whenever you can factor out that 0 in the bottom, we could write this as x plus 1 times x minus 1 over x plus 1. Sorry, x minus 1. And we are allowed to cancel those out so long as x is not allowed to be 1. And in that limit, x is not allowed to be 1. Okay. Otherwise, we would cancel those out and say this is true except for when x equals 1, and that's how we'd get that beautiful line with a hole. Okay, so algebraically, this is more the direction of where we're going, is trying to do this by algebra. Early on, to get your intuition, we'll start off by doing some tables here, and I'm going to let you go ahead and look up the table from before for that one, because this was the example we did already. What I wanted to get to, though, that usually needs some refresher is what if you have a piecewise defined function? At this point, people usually take a couple deep breaths and say, oh no, piecewise, I haven't thought about that in a while, or I've always avoided it. And we're going to need some piecewise defined functions, and they are great for creating these jumps. So let's go ahead and jump right into some piecewise defined functions. This capital H is a famous function. It is called the Heavyside Function, after a mathematician whose last name was Heavyside. It has nothing to do with his mathematician's weight. And it says, hey, if t is less... Oh, no. I mixed up my x's and my t's. Let's make these t's. Okay. If t is less than 0, then this function is 0. If t is greater or equal to 0, this function is 1. Let's go ahead and graph that. So the way you graph a piecewise defined function is by going over its domain. So t is less than 0, it's 0, which means all negative numbers, but not 0. So not including 0, it's going to be nice and flat at 0, all the way off to negative infinity. Okay, but once I get to 0, and including 0, it's going to be 1. And so now I'm going to graph this part of its domain, including at 0. Okay. So it's got this nice step function look to it. And I'll go ahead and label that scale here. This is a 1. Okay. All the way off to infinity. This ends up being really important in engineering and differential equations because this acts as an on switch, right? It's 0, so it's off, 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 and then it turns on, and it's a 1 forevermore. And this becomes a nice building block of other functions that you want to be able to model something kind of turning on at a certain time. I use these Heavyside functions. Let's go ahead and turn these to t's also. Okay, so now here's our question. What is the limit of this function as t goes to 0? Okay, take a second, see if you know what this is. All right, so the answer here is that as I come in from the right, and if I were to make a table, let's go ahead and make a quick table here, why not? Sorry, if I come in from we'll do the left first. If I come in from the left, say -1, -0.5, -0.1, well, each of these h values, they're all 0. And if I come in from the right, maybe I start at 1, and then at positive 0.5, and then at positive 0.1, I'm getting closer and closer to 0. Each of those is just going to be a 1. Okay, as I kind of scooch in here. I scooch in from this side. Okay, so we've got this issue here, which is that these are clearly all staying at 0. These are clearly all staying at 1, and they don't meet. They don't agree. Okay, and if they don't agree, what that's telling you in a graph, or what the graph is telling you, is if they don't agree, it means you've got some kind of a jump here. Right? You've got a gap, something called a jump discontinuity. But if the two sides don't agree, then we're going to say this thing does not exist. To have a limit, the two sides have to exist, the left and the right side. And so this Heavyside function has limits, beautiful limits, everywhere except at 0. Right? Anywhere above 0, it would have been a 1. Anywhere below 0, it would have been a 0. But at 0, we've got this jump, and that limit doesn't exist. So this is a case where we're still kind of out of luck. And we're going to need to invent some more notation to talk about the two different sides of this. That is coming up next. In the next section, one-sided limits. So let's go ahead and talk about one-sided limits. Sticking with this Heavyside function, I want to, in some meaningful way, talk about what is happening to the left of 0 and what is happening to the right of 0. And so we've got a left-hand limit and we have a right-hand limit. And our notation for this is just a superscript. So x is going to 0. Negative means from the left. Down here, x is going to 0 with a superscript, a plus, means from the right. Okay. And what this means, this left-handed limit, with that little negative there, means only consider the left side. I don't care what's happening with numbers, in this case, bigger than 0. I only care about numbers to the left of 0. And the right-handed limit is saying only consider the right side. Okay. And notice neither of them care what happens at 0. Limits always ignore that actual x value. But just consider the right side. Okay, so maybe you can figure this out. See if you know what it is. But I'm going to go ahead and tell you right now anyway. If I come in from the left, this little minus sign means from the left. Well, what we said before is from the left of 0, I'm staying on this 0 part, and so I should get a 0. And if I come in from the right, I'm up here. I'm staying with positive numbers, and I'm always a 1, so I should get a 1. Okay. So what you're seeing here is that even though the limit doesn't exist, the left-hand and the right-hand limit exists. So this is just more ability for us to communicate what's happening. And what we're going to see in a second is that if a limit exists, it has to have the left hand and the right hand agreeing. If the left hand and the right hand don't agree, then the limit doesn't exist. Okay, cool. Let's go ahead and take a shot here with a couple of... you'll even see that theorem ahead of time. Take a shot with a couple of one-sided limits involving graphs. So let's look at this graph here to the left, and let's say that we care about the limit as x goes to 1 from the left, and we'll just call this thing f of x. And I care about the limit as x goes to 1 from the right. And let's go ahead and say that we also care about the limit. Pretend that these pretend these beautiful open circles are actually on the grid. I did my best. Let's say that the limit as x goes to 3 from the left. I'll do one more. The limit as x goes to 3 from the right. Worth taking a second seeing if you know the answers to these. All right, so as I come in from the left at x equals 1 right here, that means I only care about the part of the function that is to the left of 1, which means that I'm going to approach this y value of 2. Oftentimes reading limits from graphs is tricky at first, but I hope that it actually becomes one of the fastest, easiest things for you. So I recognize that it's a little weird at the beginning, but your goal is to make these very, very quick, because in the end, all that a limit can do is fill in a hole or tell you what a function value is, and all that a one-handed limit can do is just tell you what happens to one side of a given value. So let's do this right-handed limit. As I approach 1 from the right, looks like that y value is going to -1, because I just care about this area over here. I get to ignore that whole left-handed thing. Okay, next up, going to 3, pretend that this is actually on the grid. Sorry. As I go to 3 here from the left, it looks like my y values are going to 0. And as I approach it from the right, it looks like they're also going to 0. Notice we really don't care about this floating dot up here because we ignore that one actual x value. Okay, so this is pretty special. If the left and the right agree, then that tells you that the limit as x goes to 3 is also equal to 0. Okay. And in fact, we've got this beautiful theorem that I've been ignoring here, which tells us exactly that. So let's walk through this theorem. I wrote it out in a little bit of small math notation. It's good for you to get used to this, and it helps you not write as much in your notes. So what this theorem says is that my limit as x goes to a of f of x equals L, which is telling you two things, that it has a limit and that limit is L. So a little sneakily telling you two things. That this is true if and only if, which we abbreviate IFF. If and only if means that this statement is equivalent to the statement down here. They are the same thing. I can even put some parentheses down here. These two things are the same. So I have this amazing limit if and only if the limit as I approach a from the right is equal to the limit as I approach a from the left. I lost an F here. There we go. And those both equal L. So I only get a limit if the left and the right agree. And that whatever that limit is that they agree on is this overall limit. We saw up here, I could have a left and a right limit. I usually have a left and a right limit. If they don't agree, then I still have a left and a right limit. I just don't have this overall limit. And so that is a really useful theorem, especially when we have any kind of a piecewise function. So whenever you have a piecewise function and you're trying to evaluate it at one of these spots where the domain breaks, what you have to do is check out the left side and check out the right side and see if they agree. And we'll get more examples of this as well. Okay, believe it or not, we've got a little bit more to go in this section, but this is a surprisingly powerful theorem. And not only that, it's starting to get to more of that ability to communicate some of this, these complicated math situations that can seem oddly specific, but we need to get really specific if we want to build all of calculus from a couple of important building blocks, like limits. All right, thanks. Next up, we'll start talking more and more about infinities.